Welcome to lecture 8. Before starting this section, I want to thank industrial personalities who learned, used and designed a new class of refractory for their organization. It is a real pleasure for me. I always try to provide ready-made literature for everyone, but sometimes slides become very busy. We have covered 9 essential properties and probable computational research in refractory development. Most of us read heat and mass transfer at different levels of education. I will briefly recap how this knowledge can be employed in refractory development. The processing of economic raw materials, firing of refractories, and heat distribution in application demand a brief discussion of heat transfer mechanisms, which will be covered here. This slide will emphasize why a basic understanding of heat and mass transfer is required while developing refractories. This figure represents heat and mass transfer are required in all 3 sectors: refractory processing, production and application sectors. Atomic arrangement defines solid, liquid and gas states and possible separation under heat, which are the fundamental aspects for the heat transformation. The inset image represents a school level understanding of conduction, convection and radiation mechanisms that need to be considered for heat transfer. We can start with the difference between temperature and heat. Temperature measures the quantity of energy influenced by the molecules of a material or system and predicts both the degrees of hotness and direction of heat transfer, whereas heat measures thermal energy transfer from a hotter body to a colder one. The units are degree centigrade and joule. Non-uniform heat distribution and low temperature in kiln results in immature raw materials and hidden regions of refractory failures in operation. For example, porosity and phase transformation of bauxite and spinel are important concerns. Organic binder develops initial stage binding in refractory particles, but high temperature facilitates ceramic bonding in a predefined temperature to avoid defect-free refractories. So, that means a prerequisite temperature is required to attain definite bonding and phases of refractories. Precast and castable lining demands preheating to achieve desired life of vessel, and process efficiency depends on refractory properties. Argon gas purging facilitates homogeneous molten steel composition and temperature in vessel. Thus, multiphase heat transfer differs from heat transfer in a single phase environment. Heat loss from steel vessels either through the open space or refractory lining is common issue. Heat control mechanism is a big deal to avoid energy loss. So, while we are considering the heat and mass transfer phenomena, we can see each and every aspect starting from the raw material processing to application. We have to think different level of heat transfer and which strictly control the refractory performance. While we consider the heat transfer phenomena predominantly conduction, convection and radiation, all 3 depend on hot surface area and their temperature. Thus, monitoring to minimize the energy loss with consistent performance of refractories is essential. Conduction initiates when high temperature aggregates molecular energies, and collision facilitates energy transfer to adjacent low energy molecules that develop thermal gradient and heat flow from higher to lower temperature. Steel has the highest and HDPE polymer has the lowest conductivity, and it follows the equation this. Convection flux depends on the random motion of adjacent fluid molecules, where H is not a physical property of the fluid, but depends on the flow patterns determined by the fluid mechanics and thermal properties of the fluid. Two types of convection, natural and forced convection. Radiation is an important heat transfer mode in an industry where material emissivity has a significant role, including surface area and temperature. Complete black body has one, and so on. A brief representation of heat and mass transformation has been pointed out here. Temperature difference in a medium is the prime driving force for heat transformation. In the same concept, the concentration gradient of chemical species facilitates mass transfer. In the case of refractory research, the convection analysis between the fixed solid surface and movable fluid is more important than bulk fluid, while refractory interaction is with molten material like steel and slag. The molar mass flux of species depends on the difference between the boundary surface concentration and the average concentration of the diffusing species in the moving fluid stream. The table gives competitive fundamental aspects of heat, mass and momentum transfer. A rotary kiln is essential equipment for making raw materials. Thousands of literature is available. I have picked up certain images and videos for better visualization, and relevant reference is also given. During processing and conversion of raw material feeding, all three processes are active, where different combinations may happen. Combined radiation and convection from hot gas to wall, heat transfer from the outer wall to surroundings, hot gas to solid bed surface heat transfer to by convection and radiation, inner wall to solid bed heat transfer, inner working lining to the outer shell through conduction. The gradual heat transfer towards the bed is prime objective. An animated view is shown in the figure, where the feed is gradually heated up through different heat transfer mechanisms. Red color indicates maximum temperature, and the feed is being gradually transferred to high temperature. The last slide discussed the probable heat transfer within the feed in kiln and throughout the equipment. A detailed heat transfer process for firing in the tunnel kiln can also be pointed out. A typical tunnel kiln cross section consists of a refractory lining pattern. The refractory loading pattern in the card is in the figure. A prerequisite temperature may assist in developing proper firing. that eventually develops ceramic bonding strength and defect-free refractories. Thus, herein pointed out all probable heat transfer processes during firing, for example, radiation and conduction between the loaded refractories, radiation and conduction between the refractories of car and load, radiation between the outside loaded refractories and the kiln structure inner surface, convection inner and outer of the loaded refractories with the gases due to combustion, radiation between the surface of the car and base of the kiln, convection between car and kiln curvace, effective conduction between kiln walls, convection between inner surfaces of the wall and flowing gases inside the tunnel, radiation and convection between the walls, outer surfaces and the environment. Control over fuel consumption and maintaining the desired kiln temperature are always challenging tasks. Thus, insulation is mandatory to achieve the desired temperature with minimum fuel consumption. A typical competitive study shows that the same kiln may have a maximum temperature of only 900 degrees centigrade, whereas insulation may boost up to 1300 degrees centigrade. However, insulation quality and thickness critically influence achieving the desired temperature profile. Here, heat transfer mechanisms for raw material processing and refractory processing are already discussed. In this slide, a typical steel ladle lining consisting of metal slag working zone magnesia carbon, backup LCC 70 and flow control refractories experiences heat transfer phenomena during different operational conditions. Uninterrupted operation without delaying ladle engagement is always challenging for steel melting shop. Several unavoidable issues such as delay in ladle lining, different preheating sequence, empty ladle or idle time may severely affect the delay operation that eventually changes the temperature profile of refractory lining and affects refractory life. A typical temperature profile variation for different preheating times and empty ladle indicates such variation. Consider an empty time of 30 minutes, after which the hot phase temperature has fallen significantly, but temperature profile in the working lining is still high. That is, it explains the temperature difference almost 200 degrees centigrade. Immediate preheating is mandatory to increase the hot phase temperature by flame temperature. So, while we are considering different preheating schedule, the mode of heat transfer has bit of difference. Safety lining and working heat content remain virtually unaffected. Heat loss to the surroundings occurs through the steel cell in this zone. Preheating in time is mandatory to maintain the hot phase temperature by decreasing flame temperature. I have picked up a video from YouTube for better visualization and understanding. Reference is also given, where an animation really presents a mode of preheating and subsequent heat transfer. Thus, again, maintaining surface area and temperature is important phenomena. This is the schematic when the preheating is being done in this mode, not the vertically. A typical example of the necessity of refractory lining optimization is shown in figure. Optimization design and lining pattern are important in the perspective of effective operation practice and energy efficiency, and optimum thickness enhances the refractory life. For example, low insulation thickness may facilitate the buckling of steel ladle and hot spot on the outer shell when the temperature is more than 300 degrees centigrade. But more insulation thickness can overheat the working lining, thus rapid oxidation and corrosion of magnesia carbon brick in contact with steel. This is the issue of refractory quality and lining importance. Usually 50 degree centigrade increment of working lining temperature may boost the refractory's double corrosion rate, that is the steel process importance. Slag metal intermediate zone hotspots may be developed due to pocket formation. The thickness of the lining may vary, because of this it happens. Strict fitness for service guidelines for steel vessels must be maintained to provide the plant safety, including assets and public health. Knowing accurate thermal property and convection radiation boundary conditions makes it possible to predict temperature profiles under various conditions with reasonable accuracy. Ladle cell temperature can be protected and avoided buckling, as well as overheating by proper backup lining. Thank you for your time and attention. I hope you found this literature informative and thought-provoking. I wish you all the best in your future endeavors. Please get in touch with me for further explanations if required. Encountering with your knowledge and interest in the next time. Have a nice time ahead. Thank you.